Okay, we have learned the overview of bolted joints and how the fasteners play a crucial role in the design. Now let's do a workshop on how to set up the model for one such assemblies where the bolts play a vital role in transferring forces across the system. We picked the model of enclosure for rear axle in a tractor. The enclosure plays the important role in housing the transmission system and the transmission fluid, but the scope of this workshop is just to set up the model with all the bolts and see if they are able to transfer forces from one end to another. Geometry has a total of 43 parts, of which 3 parts make up the enclosure, and the rest 40 parts contain 2 sets of bolts that are holding them together. Before we start setting up the model or even opening Ansys Workbench, it's worth spending a few minutes to understand the geometry, the application, and the plan of modeling strategy accordingly. Here's the geometry of the bolt. As you can see, it has bolt head, a bolt shank, and the section that represents the threaded portion. So we can use a bounded contact between the enclosure parts and the threaded portion of the bolt to mimic the threaded joint. We'll use a frictional contact between bolt heads and bolt shanks with the enclosure parts, as they are not welded or glued either. So each bolt will have 2 contacts, one bounded for the threaded regions and one frictional at the shank and the bolt head regions. Typically, we would model the 3 parts of the enclosure as flexible, as the flexibility of the parts can affect the load path of the force and how the bolts will carry the load. Also, we would usually include the preload of the bolts, but we have not discussed the topic yet. So to get acclimated with the mechanical user interface and to learn some productive tips, we'll treat the 3 large parts as a rigid to simplify matters and to reduce the computational time. For loads and boundary conditions, we are going to use fixed support and we are going to apply a force of 2000 newtons downwards on the other end. In the presence of bolts, this applied force must be transferred and balanced by the fixed end. And since all the forces are supported to balance each other out, there should be no inertial effect present in this structure. So we'll use a static structural analysis to calculate the reaction forces. With that said, let's get started with setting up the model. Start with Ansys Workbench window. Make sure that the units are set to the proper system that you intended to work with. In this example, we are going to use metric system. Next, insert a static structural module by either dragging and dropping or double-clicking it from the list. Right-click on Geometry module and go to Import Geometry and locate the file in your system. Once it is attached, let's go ahead and open Mechanical window. So the geometry is imported and everything looks good. If you expand the geometry, you'll see that there are about 43 parts in the geometry tree made of structural steel. This can be a little messy to work with, so as a first step, let's organize the geometries. Hide the enclosure part so we can see just the bolt. Now let's organize the bolts into 2 folders with each containing a set of bolts. We can identify them from the graphics window and use the box select to pick all the relevant ones in one group. Rename each folder appropriately so we can identify them easily. Now the tree looks more manageable. Next, we need to define the enclosure parts to be rigid. To do this, go to the part and change its behavior to rigid. Since there are multiple parts, we can edit them all at once by selecting them and then changing the behavior to rigid. Let's now move on the next step, which is creating the name selections. Name selections are a set of similar geometrical entities that can be created by the user. These are very helpful in quickly performing repetitive tasks and in automating several steps. In this example, we'll use the name selections for defining the contacts between the bodies and the enclosure parts and for defining the meshing controls. First, let's create a name selection for each set of bolts and one for the enclosure. Each set of bolts is used to connect two parts, so each set shares a contact with those parts. We'll create two named selections for each set of bolts, each with the parts that they are holding together. Let's start with set 1. Right-click on the name selection and insert a new name selection. Select the enclosure part and next right-click on the name selection set 1 and select Add to Current Selection. Now go back to the new name selection and hit Apply. You can see that this name selection now contains the enclosure part and all the bolts from this set. Let's name this name selection as Set 1 Bonded Contact. Similarly, select the other component and bolts and create a name selection Set 1 Frictional Contact. Now repeat this step for the other set of bolts and name them appropriately. With this done, now let's move on the next step of creating connections or contacts. If you expand connections, you'll notice that there are already several contacts defined. These are created by Ansys Mechanical while reading in the geometry. It scans through the full geometry and detects all the surfaces that are present within a distance as defined by the tolerance under details of connections group and creates a bounded contact between them. This serves us the trouble of scanning all the parts and manually creating contact pairs. However, we are still dealing with a huge number of contacts, which makes this very hard to manage. So let's go ahead and delete all these contacts and instead we'll use the same feature in a more controlled fashion. Create a new connection group by right mouse click on connections and change the group type to contacts. Right-click and rename this group as Set 1 Frictional Contact so it is easily identifiable in the model tree. Change the scoping to Name Selections and pick the name selection Set 1 Frictional Contact. By doing so, we are limiting the auto contact generation to only within these parts. Right-click and select Create Automatic Connections. This will create all the contact pairs between the enclosure and the bolt's head of the set 1. While the contact pairs are created, we need to check and make sure that all the surfaces are properly picked. We can see that all the contact pairs are created as expected. Next, we notice that these contact objects have a question mark besides them, which indicates that something not right with the definition. Before we see what's the issue, let's take a step back and learn something about contacts. The contacts have two pairs of surfaces interacting. One is called the contact side and the other is called the target side. The contact forces are calculated on the contact side with respect to the target side. So if we consider contact as a stiff spring, connecting the contact and the target side, Then the spring stiffness is calculated based on the material properties and the mesh density of the elements under the contact side. Now coming back to our model, we can see here that in these objects, the enclosure part is selected as the contact side. But we have defined the enclosure as a rigid body. So they don't have any flexible materials or elements associated, which is why Mechanical does not like them as a contact side. We can fix this very easily. Select all the contacts, right-click and select Flip Contact Target, and that will take care of it. As discussed earlier, these contacts are frictional with coefficient of friction 0.1. So once again, select all the contacts, change the contact type to frictional, and set the coefficient of friction to 0.1. Now let's set the bounded contacts for the set 1 bolts. Create one more connections group, change the connections type to contact, change scoping to name selection, and pick set 1 bounded contacts. Right-click and rename this group to Set 1 Bounded Contacts. Generate the automatic connections. Now, once again, let's inspect these contacts to see if they are defined properly. Once again, we notice the question mark, which is again due to incorrect choice of contact side. Let's go ahead and fix this. These are threaded regions, and as we discussed earlier, this will be a bounded contact, so we'll not make any changes here. With this, we have finished creating contacts for the set 1. Now follow the same workflow to create the contacts for the other set of bolts. Next, let's create contacts between the enclosure parts as well, using the enclosure name selection. In this case, we cannot use Flip Contact Target to fix the question mark because both parts are connected to rigid bodies. Instead, we change the behavior to asymmetric. This way, the solver will know which side is contact and which is target, and it will continue to using that definition throughout the simulation. The next step is to define mesh controls. The bolt geometry without the threads and with the circular head resembles a series of cylindrical portions. So to create a uniform mesh, we'll use the multi-zone mesh method, which splits the domain into multiple zones and tries to mesh them with uniform mesh. We'll define this on 2 sets of bolts. To do this, we'll create a mesh method, change the scoping method to name selection, and pick set 1. We'll change the method to multi-zone. Now repeat this step for the other set of bolts, and that finishes creating mesh controls. Before we generate the mesh, let me point out that although the enclosure parts are rigid and don't carry any mesh, they still have contacts defined on them, which makes use of contact elements. So we'll see a surface mesh created on the regions where they are sharing connections. Since this geometry has many details, it is recommended to define some mesh sizing controls on these parts for better accuracy. There are many ways for doing this, but the easiest is to define a global sizing control under the details of mesh and change the coarse angle to fine. Now let's move on to defining the loads and boundary conditions. As discussed earlier, we'll fix one end of the enclosure and apply a downward force of 2000 newtons on the other end. We'll define name selections for each end. We can also directly scope the object to geometry, but it is just a good habit to use name selections. So after creating the name selections, let's insert a remote displacement by right-click on the graphics window, insert and pick the remote displacement. Change the scoping type to name selection and pick the fixed end. Set all the degrees of freedom to 0 for a fully fixed condition. Note that we can't use a displacement condition here because the enclosure is rigid and it can only be controlled using the remote points. We can follow a similar procedure to define a remote force on the other end. We'll scope it to name selection loading end. Change the defined by component and set the y component to minus 2000 newtons as it is in negative y direction. For results, drag and drop the remote displacement to solution. This will place a force reaction probe on the fixed end. Now go to Analysis Settings and turn on Large Deflections. We do this because our model has nonlinear contacts and it is advisable to use large strain formulation for accuracy. Right-click on Solution and hit Solve. We can monitor the progress from the solver output under Solution Information. We can also visually check the convergence by changing this to force convergence. Looks like the solution is done. Now let's inspect the results. As expected, the reaction force at the fixed end is close to 2000 newtons upwards. This implies that the applied force is transferred to the fixed end via bolt connections. We can also insert the equivalent stressed object and see if any of the bolts are stressed beyond the yield limits. From the legend, we can see that the maximum stress is below the yield limit of structural steel. We can use the maximum probe to see where this stress occurs, and it appears to be in this bolt. Let's insert another stressed object, and this time we can scope it to just this one bolt. We can see where the maximum stress is building up. This way, we can use the bolted connections in assembly to study the reaction forces, and we can also check whether the selected bolt fasteners can support the load without undergoing plastic deformation. With this, we can conclude this workshop. I hope you have found this video informative. Thank you for watching, and do check out our other courses to discover more useful learning resources.